As described in the Lecture 3, in far-field microscopy, there exists diffraction limit or Abbe's resolution limit. For example, in visible spectrum, this limit is about 1 micrometer. Therefore, it is not possible to observe sub-1 micron structures or cells using visible light microscope. This can be overcome with near-field techniques by having nanoscale apertures or by using aperture-less techniques which enhance light interaction over nanoscale dimensions with the use of nanoscale tips, nanospheres, etc. The idea of using sub-wavelength aperture to improve optical resolution was first proposed by Singh in a letter to Einstein in 1928. These ideas were implemented into optics much later in 1972 by Ash and Nichols. As shown in the left figure, near-field light decays over a distance of 50 nanometers from aperture. Using this decaying behavior, it is possible to set up the near-field scanning optical microscope or NSOM as shown in the middle figure. To convert the near-field signal, we can employ tapered optical fiber to transport the near-field signal. In addition, as shown in the right figure, aperture-less technique can be used. In this case, near-field formation around metallic nanotip can be used to pick up the fluorescence signal. In other words, by illuminating the sample by the tip, we can collect the scattered light. In the near field, evanescent terms must be taken into account, due to the convolution of the tip and the sample. When a particle is much smaller than the wavelength of incident light, the particle can interact with the light wave. The first interaction is reflection. The second is transmission. The third is scattering. The scattering resulted from dielectric properties of the particles. The scattering is divided into two types. The first one is an elastic scattering or called as Rayleigh scattering. The second type is an inelastic scattering or called as Raman scattering. The Rayleigh scattering, scattered light has the exactly same frequency of the incident light and therefore, the momentum is conserved. This is the reason the Rayleigh scattering is called elastic scattering. In contrast, the particle can scatter light at different frequencies from the incident light frequency. Therefore, the momentum is not conserved. This is the reason the Raman scattering is called inelastic scattering. In Raman scattering, the changes in the frequencies in the scattered light is due mainly to the molecular interaction in the particle with the incident photon. As shown in the right figure, there is Stokes or anti-Stokes shift intervened by the intrinsic molecular vibration in the particles, which make plus or minus nu. The absolute value of nu is determined by the quantum mechanical properties of the molecules. Not all the molecular vibrations contribute to the Stokes or anti-Stokes shift for the Raman scattering. For example, in the case of acetylene molecule, 3 vibrational modes out of total 5 modes correspond to the Raman scattering. One is for infrared spectroscopy. For the molecular vibration associated with the Raman scattering, the polarizability must change during the vibration. For your reference, in a centrosymmetric a vibrational mode may be either IR active or Raman active, but not both. Therefore, to investigate the detailed information of molecular vibrations, we can combine infrared spectroscopy such as Fourier transform infrared, or FTIR, and Raman scattering spectroscopy. For example, we can find some the peaks are overlapped, and some are not in this spectroscopy of polystyrene revealed by the FTIR and Raman spectroscopy. Raman spectroscopy provides fingerprint of molecular bonds and crystalline structure or phonons in dependence on environment conditions through non-resonance excitation of any vibrational transitions. At the same time, method applications in real life are hindered by very low cross-section of Raman scattering. As shown in this exemplary Raman spectroscopy data, we can find some organic dye molecules' molecular vibrational modes both in anti-Stokes and Stokes regions. The peak position, peak width, and peak intensity provide unique information on the molecule itself, and their concentration as well as some chirality too if possible. Surface-enhanced Raman scattering or SERS is a phenomenon associated with the enhancement of the electromagnetic field surrounding small objects optically excited near an intense and sharp plasmon resonance. The enhanced fields excite the adsorbate or probe and the scattered radiation will again be enhanced. SERS consists in using the large local field enhancements that can exist at metallic surfaces under the right conditions, typically by profiting from localized surface plasmon resonances to boost the Raman scattering signal of molecules at or close to the surface. For the realization of SERS, some conditions should be satisfied. First, we need plasmonic metals such as gold, silver, copper, and platinum. Second, surfaces should be flat enough with roughness on the nanometer scale. Third, we need proper light source for the wavelength of excitation such as laser. By SERS we obtain experimental results including dramatically increased scattering intensity from the certain molecular vibrational modes of specific molecules much higher than other modes, mostly molecules with carbon double bonds. However, there are no enhancements for some molecules such as water, methanol, and most solvents. Due to surface selection rules, SERS exhibited much enhanced scattering intensity than bulk Raman spectroscopy for some organic dye such as rhodamine as shown in this plots. Using the plasmonic metal nanostructures, we can make strong near field around the metal structures. When the target molecules are placed in the vicinity of the metal nanostructures, they can exhibit much enhanced SERS intensity. This is due mainly to laser excitation enhancement, scattered field enhancement, and Raman cross-section. In particular, electric field at the surface of nanosphere is enhanced, satisfying a relationship of absolute value of electric field to the fourth. Plasmonic effects is a function of the distance between the molecule and the metal structures, and therefore, it is important to maintain the distance as close as possible for the dramatic peak intensity. Maximum SERS enhancement factor occurs at specific positions on the surface supporting the hot spots. For example, metal nanospora has enhancement factor of 10 to the 6, nanogap has 10 to the 11. Average SERS enhancement factor ranges from 10 to 1000 for non-optimized conditions, while 10 to the 7 or 10 to the 8 for very good SERS substrates. Along with SERS, there is another type of Raman scattering spectroscopy based on AFM tip. This Raman scattering is called as tip-enhanced Raman scattering or TERS. As the name indicates, TERS relies on the AFM tip, which holds some amount of silver nanocolloids at the apex. The silver colloid particles at the tip works as the plasmonic hotspots, which greatly enhances the Raman scattering intensity for some moles. It should be noted that we can still use the AFM in the contact mode, and therefore, it is possible to make two different images based on AFM TERS. The first image is topological or geometrical image of the surface, and the other image is chemical image of the surface, which provides intensity of specific molecules on the surface. As shown in the right figure, the concentration of the molecules can be investigated using the TERS with small resolution down to 5 nanometers and greatly enhanced scattering intensity. Therefore, TERS is one of the most advanced imaging apparatus to analyze the information of the surface and nanoscale structures. Now, I would like to deliver some perspectives on the nanophotonics. First, let us look at this market summary of nanophotonics. Although this data is about few years ago, it is still valuable to know how the nanophotonics will be prospering in future. One of the rapidly growing market for the nanophotonics is communication passives. This sector is for chip interconnection and passive components. The other sector is biochemical fluidic chips for the sensors and detectors. And please look at the lasers for the biomedical tools.